So our next topic we're going to talk about will be enzymes. So most of our enzymes are proteins, all are catalysts. They're catalysts by the strict definition of catalysts, and we'll talk about that in a few minutes. They're not used up in a reaction. So when we do a reaction, say we have whatever reactant, it's going to go to product or products, and we have our enzyme. We're going to have the same amount of enzyme when we're done as we did when we started. So it's a helper but not a participant in the reaction. Enzymes are highly specific. So this is going to be the beginning of our conversation about specificity. They're not only specific in what they make, they're specific to their reactant or their substrate. We'll use them kind of interchangeably, which isn't 100% correct, but not uncommon to do. So it's specific to the reactant or the substrate that it acts on. It's specific in the product it makes. It's also specific, the specificity also applies to what activates or inhibits an enzyme, because we can turn these enzymes on or off, if you will. So we can take that enzyme, activate it, or inhibit it. Enzymes do not change the Gibbs free energy of reaction. So remember from general chemistry, we had the Gibbs free energy of reaction, and that was the Gibbs free energy of the products, minus the Gibbs free energy of the reactants. So that'll get important in a few minutes in the sense that it's a product minus reactant calculation. Enzymes, like we said, can be inhibited by specific molecules. They also have cofactors or coenzymes. So you can look at the cofactor or the coenzyme as a helper. So the enzyme's the helper to the reaction. The cofactor or coenzyme is the helper to the enzyme. So all the reactions in the body are mediated by enzymes. What you're probably wondering right now, so I'll answer it, even though all of the reactions we're going to talk about are mediated by enzymes, you don't have to know every one of them. We'll talk about which ones you do need to know and the particular significance of them. Enzymes increase the rate of reaction. That's huge. They get you to the same amount of the same product to the same equilibrium. They just get you there faster. They also remain unchanged by the overall process. So let's talk about that for a minute. When we're in the regular classroom, usually at this point somebody will raise their hand and say, hang on here, you said they're a catalyst, and I did stuff with catalysts, and I had to regenerate my catalyst. So that means it changed, didn't it? And my answer to you is still no. When you regenerate a catalyst, think about what you were doing. You probably just heated it up to a really high temperature and cleaned it. So when I say enzymes remain unchanged, I mean structurally, conformationally, they're unchanged. Getting dirty doesn't really count as a change. So when you're regenerating a catalyst, we're still calling that unchanged. Chemically, it's unchanged. Among all the reactions that among all the reactions that could happen, the enzymes will determine which way you're going to go. So you might have one reactant that can go, 3 different ways. Whatever enzyme we have active or activated will determine that. So we might have an enzyme activated, take it as this way, and then these two shut off. So we can't go those two different directions. So what that means is the enzymes, or which enzyme is active or not active, determines or dictates what processes, what reactions, and what processes are going to happen in the tissue, in the body. So we're catalyzing all metabolic events, but we're doing it very selectivity. What enzymes we have determine which way we're going to go. We might have these three options, but might not have enzymes for these two. So that means we're going to go this way. Okay, we have 6 different classes of enzymes, and we're not going to get into them too deeply, but this is a little bit, or will be a little bit, of a talk in off the ledge kind of speech or thing when we get there. One of the things that it's really, really important for you to do and for me to help you do is for you to systemize you. If you don't do that, what you're going to have, particularly next trimester, is what's going to feel like a million different reactions doing a million different things, and it'll all feel very random. And it's not at all. We're going to have actually 6 different reactions on a lot of different reactants making different products. So when you're feeling like you have a million different reactions going different directions, that's when I'll remind you, no you don't, you have 6. And these 6 reactions are just things you're doing on 6 different, or on different substrates or reactants. So then the next step in systemizing you is recognizing that these 6 different kinds of reactions each have their own kind of enzyme. So these are our 6 enzyme classes. So when we start categorizing the reactions, we'll categorize the enzymes that go with them. So a couple things about enzymes. We have recommended names, we have systematic names, things like that. But when you really start digging around in enzyme names, what they are is, first part of the name will be what the enzyme does, or what it does it to, with A's, ASE on the end. So the enzyme name is what it does, or what it does it to, A's. So that kind of works. That's kind of convenient for us. So let's look at the first class. We have oxidoreductases. We're going to do a lot of oxidation reactions. We're going to have a lot of reduction reactions. What's interesting with oxidation and reduction is you can't do one without the other. So I can't oxidize something without reducing something. I can't reduce something without oxidizing something. If you remember from general chemistry, and we'll go back over it and remind you, is that oxidation is losing an electron, reduction is gaining an electron. Well, electrons like to travel with protons and make hydrogens. So our oxidoreductases are actually dehydrogenases. And we're to say goofy little things like chase the H's. But you're going to be able to use this 2 ways. You're going to use it to help you remember reactions, and you're going to use it to help you remember enzymes. So here's what I mean by that. You might have some reaction that you can't remember what the enzyme is, but you know the reaction's an oxidation reduction. So you know that the enzyme has to be a dehydrogenase. So it's got to be a dehydrogenase, and I know the first part of the enzyme name is what it does or what it does it to. Then I have the A's on the end. So I know I'm going to have a dehydrogenase if it's an oxidation reduction, and if it's lactate that I'm either using or making, lactate dehydrogenase makes perfect sense. So that's our backwards forwards using it that you'll be able to do. Another type of reaction that we'll do is a group transfer, and the enzyme that catalyzes that is a transferase. That's kind of nice. How much more descriptive does it get than that? We'll bring in a little, I think it's Latin. When we're moving, say, a phosphate, that's always going to be a kinase. And I'm not 100% sure that came from Latin, but I think it did. We're going to have hydrolases. Hydro something reactions are pretty obvious. The two we're going to do are hydrolysis and hydration. They involve water. So we're doing things with water. They're going to be our hydrolases. So we'll see the enzymes that do that. We're going to have lyases. Lyases add or take away groups to make double bonds. So that's another thing we'll be doing, but you'll get pretty tuned into, well, if I see this enzyme, this is what I'm doing. Or if this is what I'm doing, this is the kind of enzyme that does it. We're going to make isomers. So we're going to do isomerizations. Isomerizations. Properly said isomerization. The enzymes that we'll use to do that are isomerases, isomer with A's on the end. We'll also really dig down on some of our enzyme names. So if you look at this one, it will break down all of these words. I have an isomerase, so I know I'm making an isomer. If you remember, and we'll go back over this, but if you remember, when I make an isomer, I'm not going to add anything or take away anything. I'm going to have the same parts of the molecule. I'm just going to rearrange them. So here, I know I'm rearranging. That's it. Not adding or taking away anything. Another thing we'll come to is we're going to learn that ose means sugar. If something ends in ose, you're going to get your brain on sugars, on carbohydrates. Tri sounds kind of three-ish. It is. So I've got a 3-carbon sugar here. And I have a phosphate attached to it. I'm not adding or taking away anything. I'm going to keep my 3 carbons. I'm going to keep my phosphate, and I'm going to rearrange them. So that gets important. Now it's kind of, okay, whatever. But that's going to get really important when you just feel like you have a million reactions, a million molecules, everything swimming around in your head. And we'll talk about how you start to feel like that, even though you really won't have a million molecules. It's a lot to do with a lot of them sounding very, very similar. We can have ligases doing ligation reactions. So we're going to have 2 substrates, use ATP, and we'll talk about that one too. But again, forwards, backwards. This is the enzyme. This is what I must be doing. Or this is what I'm doing. This has got to be the enzyme that's doing it. So we'll come to all that. But for now, know that my enzyme name is what I'm doing or what I'm doing it to with an A's on the end. So enzymes are A's. That ose is our sugar. Okay, so we said we can have an enzyme, and our enzyme needs a helper, and we didn't get into what our helpers are. So if my helper, and the enzyme's protein, so we'll say sometimes non-protein moiety, and there's certain terms that I just want you comfortable with, even though I don't know the odds of you actually seeing it. But the non-protein moiety, the other thing attached to the enzyme, its helper, if it's a metal ion, we call it a cofactor. Well, where am I getting a metal ion? Remember your vitamins and minerals? We should really be saying, instead of vitamins and minerals, we should be saying vitamins and ions. But I guess ions doesn't sound as good as vitamins and minerals, so we say that. But my minerals, of my vitamins and minerals, is a metal ion. That's my cofactor. So that's your minerals. And we're going to see these. The first one we're going to use is a magnesium. And we'll talk about the enzyme that has magnesium as a helper. If the non-protein moiety happens to be a small organic molecule, we're going to call that a coenzyme. Small organic, it's really a vitamin. So if I have a mineral, I call it a cofactor. If I need a vitamin, I call it a coenzyme. A couple of those that you're going to see pretty often are things like vitamin B1 or thiamine. We're going to use that in a lot of reactions. Particularly, we're going to see that in decarboxylation reactions. If you don't know what a decarboxylation reaction is, no problem, we're going to come to that. We're going to have niacin when we're carboxylating. Biotin, I should have said. We'll have niacin later. We're going to have biotin when we're carboxylating. We're going to have niacin, getting ahead of myself, and riboflavin when we're doing a couple of particular energy making reactions or energy moving reactions. So we have a couple more definitions, and we are going to try to keep your definitions to a minimum. If I have the enzyme with its helper, whether it be a cofactor or a coenzyme, I call that the whole thing. So I put whole O in front of it. Remember, with your terminology, with your medical or scientific terminology, if we put A in front of anything, it means without. So we put apo in front, it's my enzyme without its helper. Okay, a few examples, and don't worry about learning this table. You will. You'll learn it the best way without meaning to. So these are all coenzymes and cofactors. We could say cofactor here. These are all coenzymes and cofactors you're going to see with the particular enzymes to which they're the helpers or for which they're the helpers. So we'll go through and we'll do that. Okay, really, really important. Enzymes alter the rate of reaction. So they increase the rate of reaction. That's what they do. So that's important. They don't change the equilibrium. So you're going to get the same amount of the same product, you're just going to get there faster. So if it's a reversible reaction, when I say product, I mean the result of whichever way you're going. So if A is going to B, you're just going to get more B, or you're just going to get the same amount of B, but get it faster. If B is going back to A, you're not going to get more A, you're going to get the same amount of A, just get there faster. So I get to the same equilibrium, I just get there faster. Okay, so we have what's called an enzyme substrate complex, and we're going to get into some detail of that. But what happens is I have my enzyme, my substrate binds to what's called the active site. So it binds to a spot on the enzyme that's meant for it, specific to it. That's where my specificity comes from. So it binds there, becomes the product, and goes and does whatever it's supposed to do. So this idea of the active site is, like we said, where our specificity comes from. So I have my enzyme, and the big blue blob is my enzyme, and I have a spot on it that my substrate, my little red blob, is the substrate that it fits into. So when it fits in, it might make little conformational changes, but only the substrate that's meant to fit on that enzyme fits. So the substrate will go to its little spot, its binding site, its active site. There's your enzyme substrate complex when it goes there. The substrate will become the product, and then it'll dissociate. It'll take the product, send it on its way to do whatever it's supposed to do. So we've alluded to this a little bit. This is our lock and key model. So this is one way of explaining that specificity. So I have a lock on my front door, you have a lock on your front door, I have a key, you have a key, everybody has a key. I can't take my key and go put it in your front door and expect it to open. Maybe the key will fit, but even if it fits, it's not going to turn. Because your key is specific to your front door, my key is specific to my front door. Same idea. So this substrate is specific to its active site, or the active site, like the lock, is specific to that substrate. So that's what's going to make it fit. That's where our specificity comes from. So we'll talk about tertiary structure later, but if we have this unique, tailor-made, ready-to-fit site, that's what's going on. That's our lock and key model, our perfect little fit. We might have to have an induced fit, kind of like the key you have to jiggle around. My key fits my front door. It's made for my front door, but it's not perfect. It's one of the ones where I have to pull it out a little bit and then jiggle it and turn it, and it'll fit. So this is where, as the enzyme and the substrate interact, we got to change the conformation a little bit to get a nice snug fit. That's me jiggling that key around, pulling it back a little bit to make it fit. So the enzymes and substrates, we still have the specificity, but we have an induced fit. Got to play with it a little bit, kind of fit. Okay, let's talk about activation energy. This is what gets really important. Actually, this is cut off a little bit, so we'll go to the graph and come back anyway. So what I'm doing is I'm taking reactants that have a certain amount of energy or substrate. So on my y-axis, I have free energy. So I have my substrates that contain a certain amount of energy. I have products, or a product, one or more, that contains a certain amount of energy. In between reactants and products, I have a transition state. So back in general chemistry, when you were drawing reactions and you had the reactant and you had your product and you drew this thing in the middle that looked like a mushed up, not really the reactant, but not really the product, but kind of a combination of the two thing, that was your transition state, your intermediate, whatever. That has a certain amount of energy too. So what we have to do to get from substrate to product is we need to have enough energy to get through that transition state. So that's called the energy of the transition state. And I'll write it because I could cut off a little bit. And it's abbreviated S with the little plus plus symbol, or it's activation energy. These are synonymous. And that can be abbreviated capital E subscript A. So, only time I'm going to give you synonyms is if I think there's equal-ish probability of you seeing either. So, another abbreviation is delta G with the little double-crossed T thing. So, only time, like I said, I'm going to give you synonyms is if I think there's equal-ish probability of you seeing either. The other thing is, most often in questions, most often but not always, you're going to get the words. It's just easier, less confusion, less ambiguity, but no guarantee. So make sure you know the words, make sure you know the abbreviations or the symbols. So I've got reaction progress on my x-axis. I could cut off. So I'm going from substrate to product. To get from substrate to product, I need to have, and I could have had it the other way. I could have had the substrate having less energy and, done this kind of thing. Doesn't matter, but for our example, it just happens to go this way. So, oops. To get from substrate to product, I need to have enough energy to form this transition state. That's called either the energy of the transition state or the activation energy. So really what I've got to be able to do is I need enough energy to climb up over this hill. So let's think about it like we're riding our bicycles. Riding our bicycles somewhere, and I know it's a little hard to find a hill in Florida, but I don't know, we can go up to Claremont and they have a hill, probably the only hill in Florida. Or you can be biking down over the Dunlawton Bridge. We'll stay local. So, if I'm going over a hill on my bicycle, that's going to slow me down, right? If I'm going a nice flat 5 miles, even I can go pretty fast on that. If you stick a hill in the middle of my 5 miles, I'm going to slow down. So, if you want to speed me up on my bicycle, how about, instead of making me climb up over this hill, how about we lower my hill? And I've only got to go over this hill. So you flatten out the hill I have to ride my bicycle over. I'm going to go faster. That's really what we're doing here. We're flattening out the hill, lowering the amount of energy that I need, lowering the hill I've got to get over, and I'm going to go faster. So what an enzyme is really doing is it's increasing the rate of reaction. Really important that you know this. It's increasing the rate of reaction. How is it doing it? It's doing it by lowering the activation energy, or saying the same thing exactly the same way, lowering the energy of the transition state, lowering the hill I've got to climb up over. Because it's lowering these things, making it easier, making it quicker, that's how it's increasing the rate of reaction. So let's talk about questions for a minute. And soapbox moment for a second, but in our software, we can see the stats on every question you're ever going to answer. And those stats are so useful. And they're not just useful in the sense of I can see how many get a question right and how many get a question wrong. I can look at the format of the question and kind of see what's going on. And what I mean by that is I might ask you the same concept 2 different ways, and the stats come out very different. So if I ask you what do enzymes do and give you a bunch of options, and the options are, increase the rate of reaction, lower the activation energy, lower the energy of the transition state, that usually goes well. If I ask you what do enzymes increase or what do enzymes decrease, and give you the whole list, the stats drop a little bit. So I think what happens, based on your predecessors going over tests later, is I think you kind of don't quite read it. You read one thing and see something else. If I had $1 for every I read it wrong I get, I'd probably be on a beach sitting under a palm tree somewhere right now. It's just so common. And I think it's worse to get a question wrong because you read it wrong. It's one thing if you just don't know the material. That, I don't know, somehow that's not as painful as knowing your stuff and then reading it wrong. So my point is be very careful reading the question. Is the question asking what do enzymes do? They do all of these things? Or what do enzymes increase? They increase your rate of reaction. Or what do they decrease? They decrease activation energy, or they decrease the energy of the transition state. So again, that part's not difficult, But depending on how the question's worded, and not that they're worded in a difficult way, but if you start reading fast, it's really easy to miss what you're looking for. Okay, some things affect reaction rate. And some of them we're going to use and do things with, some of them we're not. So we said enzymes increase our reaction rate, increase our rate of reaction. Some of the things affecting our reaction rate, though, are on top of that. Enzyme kinetics are affected by temperature and affected by pH. True, but kind of not going to affect us. We're assuming constant temperature and constant pH from here on in. Enzyme concentration is a factor that affects our reaction rate. So how much enzyme we have is a definite factor. Substrate concentration. The rate can be increased by adding more substrate, sometimes to a point, or by removing the product as we form it. So we'll talk about both of those things. One of the things we're going to talk about is enzyme saturation. So we can look at, look at a group of enzymes like a bus. We only have a certain number of seats on that bus. Look at the seats on the bus like all of our active sites on all of our enzymes. When we have all of those active sites filled up with substrate that will form the enzyme substrate complex that will then form product that can dissociate. When we have all those seats filled up, we're going to call the enzyme saturated. Like if we have a bus and all the seats are filled, it's saturated. And we're going to use that in a minute. Once we're saturated, the only way to increase our productivity then is to add more enzyme. Okay, where we're going next is Micheli-Menten kinetics. We're not going to do calculations or anything like some of you have in your undergrad, but we're going to use it, talk about it, and talk about what it means to us. What does it do for us? So we have the equation here, and we're actually going to look at it graphically. When we look at the equation, there's some parts to it we need. First one is V of 0, V naught, depending on where you're from. And that's our initial velocity of reaction. That's what we start out as. Concentration of substrate. We're going to use our square brackets. We're not doing calculations, so that's okay. V max is our theoretical maximum rate of reaction. When we've got that reaction going as fast as it can, that's our V max. Km is our Micheli-Menten constant. This is the one that gets messed up all the time. So it's specific to the enzyme. It's the substrate concentration. That's the part you forget. That gets you to half of V max. I don't know how to write that. Try to abbreviate it. You're usually really good at remembering that the half of V max part, it's the substrate concentration part that you get. It's going to be on the x-axis of a graph where x is the substrate concentration. So we're going to talk about it in a minute. All right, so we're going to use a graph, and we're going to talk about Micheli-Menten kinetics. So my x-axis is substrate concentration. That's ugly. Let's rewrite that. I don't know why I cut it off on me. So my x-axis is my substrate concentration. My y-axis is reaction velocity. So we can look at this kind of like your car. You're sitting at a stoplight and you're stopped. So what's my car's job? My car's job is to accelerate, get to whatever speed I want, and take me where I'm going. How does it do that? Well, it does that by me putting my foot on the gas pedal and I go. So when I'm down here, I'm sitting at the stoplight and I'm not giving it any gas because I'm sitting there. I'm waiting for the light to change. I have no velocity. I'm at 0. Then the light turns green. I give it a little bit of gas, a little bit. Gas is my substrate, gasoline's my substrate, and I get a little bit of velocity. I give it a little more gas, a little more substrate. I go a little faster. Little more gas, more speed, more gas, more speed. But let's say, I don't know, I'm going to be a little maniac. I'm going to floor it. So I'm going to floor it, and I hit a point where no matter how much gas I give it, I'm just going to level out. I can't get it going any faster. I just level out. So really, I should have drawn this so my lines meet. That would be my Vmax. So this is really theoretical. But I should have my lines meeting. That's my Vmax. I can push on that gas pedal as hard as I want. I'm not going to go any faster. So that's kind of what I have going on, or is what I have going on here, except it's substrate, my substrate concentration, and giving me reaction velocity. So let's take a step back now and talk about this a little bit more. Let's say now I want to figure out, so let's say now we'll keep using the car analogy. So cars and money make the best analogy for science and engineering topics. We'll get to the money part. We'll use cars for now. So let's say, I don't know, let's say you've been in practice for a while and I just stopped by to see your office and we're going to go to lunch, but you're busy with patients right now. So you say, you know what, I'm going to be tied up for another hour or so. I just bought a new Lamborghini. Do you want to take it for a ride and check it out? I say, okay, let's do it. All right, so what I want to know with your Lamborghini is how fast can I get it going? So I'm going to start out at the traffic light. I'm going to give it a little more gas, a little more gas, a little more gas, and see, I go, I don't know, 0 to jail when. So I do that. And what I want to know is where did I hit this Vmax point? I don't know. So what can I do? I don't know where I leveled it out. But what I want to do is go tune your Lamborghini and see if I can get away from that light even quicker. So I need some kind of comparative term to do that. So where it's a comparative term, I kind of don't need to know where I leveled out exactly. What I can do is I'll go and see how much gasoline did I need to get to half of Vmax. So I'll look at half of Vmax and say, oh, here's how much gasoline I needed. And I'm going to call that Km, that's my Micheli-Menten constant. That's the substrate concentration. It's on the x-axis here. That's the substrate concentration that got me to half of Vmax. All right, so I've got a reference point now. So okay, you're still busy with patients, and I'm still running around with your Lamborghini. So I'm going to go tune it up. And I'm going to try this again. So I'm going to get to that traffic light. I'm going to floor it. So here's what I get. Give it more gas, get up and level out. Is that better or worse? Where did I level out? I don't know. So let's do that comparative thing. If I look at what got me to half of Vmax, I'll go over and say, This is my new Km. Did I do better or worse? Well, I got to the same thing, half of Vmax on less substrate. I must be doing better. Again, comparative term, new reaction conditions, if it were a reaction. Because Km is the substrate concentration that gets me to half of Vmax. Lower Km means less substrate, means in the car thing, more efficiency really. In an enzyme and a substrate, it means higher affinity. And we'll talk about that in a minute, how well that substrate binds to that enzyme. So I could keep going and play with the car and see what other curves I get. But again, Km, the substrate concentration that gets my job done, my job as I just defined it, is to get to half of Vmax, is my comparative term. Okay, so we just spent the time doing that, talking about cars and all that, with something you could memorize if you wanted to. Don't, it's just making your life more complicated. So on this graph, my Km would be here, and my substrate concentration is my x-axis. So if my Km is low, that means I'm lower on the x-axis, which is substrate concentration. So I used less stuff, less substrate to get the job done. That means I have higher efficiency, kind of a casual way of saying it. But with enzymes, the word for efficiency is affinity. You can look at that as how well the enzyme and the substrate like each other. It's really how tightly they bind to each other. Higher affinity means they're binding better, more tightly. Or if I have a higher Km, that means it's my curve, over here. Oops. Higher Km, I need more substrate. So just like your car, let's say, we'll talk gas mileage. Let's say I need more gasoline to travel the same distance. My car is running at a lower efficiency. In enzymes, efficiency is affinity, lower affinity. My enzyme and my substrate are not binding together as well. It's a weaker binding. Then I'm going to need more substrate to get the same job done. So low Km is high affinity, high Km is low affinity. Much easier to think about cars and go through the story we just did than to try to memorize it. The other thing, and I know you know this, but let me remind you, with memorizing, the worst memorization is the either or kind. It's much easier to memorize a list of 5 things and remember it than remember either or kind of memorizing. It's so easy to talk yourself into, well, low Km. Does that mean higher or lower? The more you think about it, the more you confuse yourself. So, like I said, much easier to think about and remember the car stories. I know some of you, as we were doing this, were thinking, all right, come on, what are we doing this for? Just apply, y equals mx plus b. Did it a million times in college algebra and everything. And you can, and if we had a lab, we'd be doing that, but we don't. But if you apply y equals mx plus b, you can look for the intercept, figure out the slope and everything, and do it that way. That's called a Lineweaver-Burke plot. Okay, next thing we're going to talk about is we're going to talk about inhibiting enzymes. So let's do a quick little example so you know where we're going with this. Let's say, just for an example, let's say I get up this morning and I eat a molecule of glucose. So I had a, bagel or something, and it contained glucose. Well, glucose can go a number of different directions, but we're going to stay very simple and talk about a couple of them. I can make energy out of it. I know I really should be saying storing energy, but it's a habit saying making energy. That's okay. Or I could store it. So, what do I want to do when I get up this morning? Let's say I didn't eat since last night. So, what I want to do is I want to direct that glucose to where I need it to go. So, what I'm going to do is I'm going to activate enzyme 1, like I'm opening this valve, and send that glucose to energy. I'm going to inhibit enzyme 2 so it doesn't go to storage. So I'm going to do that. I haven't eaten all night. I need energy for my cells. I'm going to send that glucose where I need it. An awful lot of the time when you're asking, well, what do I do here? What's happening? I'm going to say the standard biochem answer. It depends. It depends usually means it depends on what the cell has and what the cell needs. If I haven't eaten for 12 hours, it needs energy. I'm not worrying about storing. So I'm going to do that. Then I'm going to keep eating. I'm going to have another bagel. It's really good. And another. And another. Because they were really, really good. What's going to happen then? Well, at a point, I've got my energy needs taken care of. I'm going to store. I'm going to store the carbohydrate, or I'm going to make fat or whatever. Now, I need to close this valve, shut off the energy side, inhibit that enzyme, and activate this one so I can send bagel number 3, 4, 5, 6, whatever, to storage. So that's the concept of activating and inhibiting. As we're going through it, we're going to talk about focus more on inhibition, turning the enzyme off. Okay. Within Micheli-Menten kinetics, we have two kinds of inhibition. One is competitive and one is non-competitive. So let's draw these and kind of walk our way through them. So what I have is I have my enzyme, and it has its binding sites and so on. And I have my substrate. So I have my substrate, and what my substrate would like to do is bind on its binding site, become the enzyme substrate complex, become the product, get dissociated, be the product, and go do whatever it's supposed to do. So what I can have, though, is I can have an inhibitor. So look at it this way. Let's say when we're in class, I always tell the story this way. One of you guys will be my substrate. Your chair will be your binding site, and your reaction is taking really nice, beautiful biochemistry notes. I'm going to be the inhibitor. I get the good part where I'm the one telling the story. So what a competitive inhibitor does is a competitive inhibitor is going to take the binding site that the substrate would like to occupy. So in my story, you get up from your chair for a second to go do whatever. You're the substrate, your chair is your binding site, your reaction's taking notes. I grab your chair, I sit down in your chair, and I don't know, I play games on your computer. I update your Facebook status with, I love biochemistry, stuff like that. So what have I done? What I've done is I've shut down your reaction. I inhibited your reaction by taking that binding site, taking your chair. So because I'm in your chair, you can't do what you're supposed to be doing, your reaction, which is taking beautiful biochemistry notes. So that's my competitive inhibitor. Or I can have a non-competitive inhibitor. So I still have my enzyme. I still have my substrate, will be consistent with colors. This time, though, my substrate can have its binding site. So that's my substrate. My substrate can have its binding site. So, same story. You're the substrate, your chair is your binding site, and your reaction's taking really beautiful biochemistry notes. I'll still be the inhibitor. So here's what I'm going to do this time. I'm going to be a non-competitive inhibitor. You want your chair, keep your chair, sit in your chair. I'm going to come along and I'm going to bind somewhere else. So what I'm going to do in our story is I'm going to pull another chair right up next to you. So I'm still going to be the inhibitor. I'm going to pull another chair right up next to you. Every time you go to write or type, I'm going to take my bony little elbow and kind of give it to you in the ribs. So you're going to type or write, and I elbow you in the ribs. I elbow you and elbow you. What's going to happen with your reaction now? Your reaction's not going to happen. I'm elbowing you or whatever I'm doing. So you have your binding site, you're there, you're in your chair, but I'm still able to inhibit from somewhere else on the enzyme. So this is my non-competitive. This was my competitive situation. So let's back up again on this story a little bit. So competitive is the most common one. So let's talk about that a little bit. Let's go back to the chair story. Now, let's say we have a classroom with, 50 students in it or something. So you're sitting there in the front row, you're the substrate, your chair is your binding site. I'm still the inhibitor, your reaction's still taking notes. So we're going to stay in a competitive situation. So in the competitive situation, we told the story first. You were the only substrate. You get out of your chair. I, as the inhibitor, jumped in it, shut your reaction down. Let's do it this way now. Let's say now everybody in the class is a molecule of substrate. You guys all take equally beautiful, wonderful biochemistry notes. So now you get up from your chair, you're going to have a stretch or a coffee or whatever, and I go for it. I go for it with sort of 49 other substrates. What are my chances now? Probably not so good, right? I think they're pretty good, but, no, really, probably not. So, no. I went from a 1 in 1 chance to a 1 in 49 chance. It's an odds game because we increased that substrate concentration. Now I've overwhelmed the effect of the competitive inhibitor. If one of your 49 other substrates got to the seed, we're going to get the same amount of the same product, same Vmax. So increasing the substrate concentration overwhelmed the effect of the competitive inhibitor. So this is competitive inhibition, and Michele mentioned kinetics, is the most common form of inhibition, and it's common with a lot of drugs. It's the way statins work. Statins inhibit an enzyme that's in the cascade that we use to make cholesterol. It inhibits an enzyme called HMG-CoA reductase. We'll come to that. And by inhibiting it, we stop the formation of cholesterol. A lot of blood pressure drugs work the same way and everything. So you're going to see this again when you start talking about some of the pharmaceuticals. So that's my competitive. My other option is non-competitive. So what can we do about that? Well, not a lot, because think about this one. Let's say now you're still the substrate, your chair is still your binding site, taking notes is still your reaction. I'm the inhibitor, I'm sitting there kicking you, elbowing you, whatever. Let's make everybody else substrates. Can that increase in substrate concentration? Can those other 49 substrates or whatever help you? No. They can hang out, but you're in the binding site. Wouldn't matter if they were in the binding site. You're there. You've got it. So no, they can't help you. So in this case, Vmax is going to decrease. The inhibitor is going to shut down the reaction regardless of your substrate concentration. So Km in this case will remain unchanged. We can increase the Km over here. So that's our story with our non-competitive. Not as common. It's used as some antidepressant drugs, stuff like that. It gets important in the breakdown of some of your catecholamines, some of the hormones we're going to talk about. We'll talk about it with a process called gluconeogenesis, using lactate dehydrogenase, things like that. Don't worry about any of that now, but just know we are going to come back to this when we're actually applying it. Okay, pretty much what I attempted to draw. So the competitive, like we said, increases the Km. We need more substrate to get the job done. Statins are one of the drugs that runs on it. Non-competitive, again, exactly what we said. There's another form of kinetics, another enzyme kinetics that we're going to talk about. We're going to talk about allosteric enzymes. So allosteric enzymes are what we're going to use for most of what we're going to do. So we're still going to have the same idea with the graph. We're still going to have reaction velocity. We're still going to have it as a function of substrate concentration. But rather than the up and over shape that we just had with Micheli-Menten, we're going to have a sigmoidal dependency this time. Remember from college algebra, sigmoidal dependency means S-shape, we're going to drag a little bit, then come up and over. So this will be our allosteric. So what I'm getting at here is completely different kinetics. So with our allosteric enzymes, we're only going to have a non-competitive situation. Meaning, I have my enzyme. That's an awful enzyme. Let's try that again. I have my enzyme. I have my substrate. It can have its binding site, and I have my inhibitor that'll bind somewhere else. So it's going to bind, sometimes I'll say in a non-covalent, a non-competitive manner. It's also non-covalent, but we'll come to that. Sometimes I'll say in a non-competitive manner, and I don't know if I should say that or not. I'm always back and forth on that. When I say that, I mean exactly what I did by non-competitive when we were talking about Micheli-Menten, the inhibitor binding somewhere else. I'm just trying to make the distinction that the kinetics are entirely different. It'll bind non-covalently. Where in Micheli-Menten, our competitive inhibitor would bind non-covalently and reversibly. Our non-competitive would bind covalently. And it's actually irreversible. So now I've got non-competitive and I've got non-covalent. So you can see where that's going with multiple choice questions too. Okay, a couple definitions we're going to talk about in a minute. Like we said, it's a sigmoidal dependency. Sigmoidal, substrate concentrations down here, got cut off. Sigmoidal is that kind of S shape. Okay, let's talk about some words, and we're going to build this story up, and everything I'm going to say was in the PowerPoint. It's just easier to draw a picture. I like drawing pictures, as you're probably figuring out. We're going to do this kind of like we did alkalosis and acidosis, figuring that part out and figuring out the respiratory and the metabolic. So I can have an inhibitor or an effector or a modifier if I'm activating, let's back up, if I'm activating or inhibiting an allosteric enzyme, I can call that molecule that activates or inhibits an effector or a modifier. And again, I won't give you synonyms unless I think there's equal-ish probability of you seeing either one, and here I do. So my effector or my modifier, the molecule that activates or inhibits, can be a couple things. If it's a molecule that activates, we're going to call that a positive effector or modifier. So that activates. If it inhibits, we're going to call it a negative effector or modifier. So that one inhibits. That's going to be half our story. Then, if the molecule that activates or inhibits is the substrate of that enzyme, then we're going to call it homotropic. So a homotropic effector or modifier is the substrate of that enzyme. And we'll talk about this more in a minute. If it's anything but the substrate of that enzyme, it's heterotropic. Okay, so what are we going to do with this? Let's say I have my process. A goes to B, goes to C, goes to D. Enzyme 1 converting A to B, enzyme 2 converting B to C, enzyme 3 converting C to D. So we said positive, negatives, really easy. If I'm activating, regardless of what's activating it, it's positive. If I'm inhibiting, regardless of what's inhibiting, it's negative. Easy enough there. Homotropic, heterotropic, easy too. If it's the substrate of that enzyme, then it's going to be homotropic. So A is the substrate of E1. B is the substrate of E2. C is the substrate of E3. The enzyme acts on the substrate and forms the product. If, say, D had an effect on E3, it'd be heterotropic. C affects E2, C affects E1, whatever, heterotropic. Got to be the substrate of that enzyme. So the way I would approach that is I would ask myself a yes-no question. Is it the substrate of that enzyme? Yes, homotropic. No, heterotropic. Done. So let's do a couple of examples. Let's say I have a molecule of glucose, and I'm going to convert it to a molecule of glucose 6-phosphate. This is actually one of the first reactions we're going to do. The enzyme that catalyzes that is called hexokinase. And you don't necessarily know what any of those are yet, and it doesn't matter. So what I'm going to tell you is that a high concentration of glucose 6-phosphate inhibits hexokinase. And you're going to tell me, is it homotropic positive, homotropic negative, heterotropic positive, or heterotropic negative? So when you get asked these in an academic environment, this will be your options. and you're going to figure out what it is. So I would be super mechanical doing this. So first thing I go looking for is activates or inhibits. I've got to give you, this information. If you want to, if it feels better to you, because you might not know what glucose and all that is yet, go A, B, E1, and B again. A goes to B, E1 catalyzes it, and a high concentration of B inhibits my E1. So I would go looking first for the word activate or inhibit. So here we go. I found it. So inhibits means negative. Then I would say, okay, well, what molecule inhibits it? Oh, glucose 6-phosphate inhibits it. Is glucose 6-phosphate the substrate? Nope. Then it's got to be heterotropic. So this one's heterotropic negative. If a high concentration of glucose, say, activated it, then it would be homotropic. Let's do another one. Let's say I have fructose 6-phosphate going to fructose 1,6-bisphosphate. And I'm abbreviating, so it's kind of unimportant what any of that is right now. What I will tell you is, let's say high concentration. Actually, we don't need high concentration. Any concentration. I don't want you to get hung up on quantity. Citrate inhibits phosphofructokinase, PFK. So, do you know what any of this stuff is? No, you don't care for this. Doesn't matter. And if you want, you can go A, B, enzyme 1. Is citrate A or B? Nope. We'll make it C or whatever. And we'll go from there. So what you're going to do is, I would go first. Go looking for the words activate or inhibit. I found inhibit. Inhibit means negative. Is citrate the substrate of enzyme 1? No. Fructose 6-phosphate is. Do you know what citrate is? No. Do you care? No. Just, is it the substrate? No. So if it's not the substrate, doesn't matter what it is, that makes it heterotropic. Okay, so that's where we needed to get to with enzymes. And let's talk about what you're going to do with this. While we're doing it now, it's feeling, of course, because I presented it that way, like a very mechanical academic exercise. And it is, and that's kind of a good way of learning it. Where you're going to actually use it, though, is the other way around. So what I want to encourage you to start doing now, even though you feel like, well, I'm only try one, I don't know anything from anything yet, think about what you're interested in. You'll hear the goofy expression, the riches are in the niches kind of thing, but if you're sitting in class, and I know you are for some of your classes, if you look around, every one of you are going to be chiropractors. What's going to differentiate you from everybody else in the room? It's going to be whatever niche you choose. Everybody's first thought is, well, I'm going to be the world's most awesome adjuster. You need to be an awesome adjuster, and you will. But everybody's going to be really good adjusters. You all need to be. What else are you going to do? Think about your particular interests. Read about them, run with it, see what chiros you can go shadow that have those interests. I know a chiropractor who, he lives for golf. The man still lives for golf. Golf is life. And if he wasn't studying, he was golfing. So that was his practice. He started working with a golf pro, and there's a whole lot of ins and outs of doing that. he started working with a golf pro. He got really, really good at treating golf injuries. And of course, working with the pro sent him a lot more golf injuries because he was so good at treating them, and he got better and got more and so on. But it was because that was his thing. What was really cool about the story is he was working with a junior that was competitive, and his parents were very supportive and everything. It turned out that this kid's dad was very involved with Titleist, the golf equipment company. He was so impressed with this chiropractor that he built and brought him out to run the Titleist Performance Institute in San Diego. If you don't know what that is, even if you couldn't care less about golf, Google it and you'll see what an incredible facility it is. But that's where his niche took him. There's other chiropractors that have run with other niches. It might be nutrition. I know a chiropractor who has a huge pediatric practice. She never thought she'd have that, but her thing was fertility work. She was very good at it and produced the pediatrics, so ended up with a pediatric practice. So start reading and thinking and everything now. I know you don't have an awful lot of time, but you have time to think. So start reading then about whatever your interest is and stay on top of the research, get on top of the research. And the research is where you're going to use words like this or terms like this. You're going to be reading something and you're going to read something's a heterotropic negative effector on whatever, depending on what your topic is and what you're reading. And you're going to back it up and say, okay, well, negative means it inhibits, and heterotropic means it's not the substrate. So something other than the substrate is inhibiting that enzyme, and as a result, causing whatever that I'm reading about. And an awful lot of the things we're doing, we're going to do kind of mechanically like this, but when you apply it, you're going to apply it the other way around. Right now, the mechanical is just kind of do it and get through it to learn it. The applying is the really interesting part. And that's why I'm encouraging you now to get reading, even if you only dedicate 30 minutes a week or whatever. Start doing it, because sometimes what we're doing now, homotropic, heterotropic, negative, positive, whatever, will get a little monotonous. But if you figure out what your niche, your thing is, and you spend some time reading about it and learning about it, and the best part is, if you can find a chiro who's doing that and go shadow them, that's kind of what makes it worth it and makes the kind of the drudgery of homotropic, heterotropic feel better. So it's very much worth your time to go and do that. Other thing with the shadowing, go do it. You need to be, whenever you have time, you need to be hanging out in chiropractors' offices, and a variety of them. Even if your parents are chiros and you were in their office in diapers, you still need to be in other offices. See what you're getting yourself into, see how different offices are run, see what they're doing, see what you're going to be doing. And what you're going to do is, there's going to be offices that are doing things you like, there's going to be offices that are doing things you don't like. And you learn just as much in the ones that you don't like, because you learn you don't like it, and that's what you don't want to do. So it's really important when you have some free time, and it may just be over the breaks, go and shadow. And you can shadow the same office now and go back in a year and see something entirely different because you know more stuff then. And watch not only how they adjust, you just zone in on that, but watch how the office is run. What else are they doing? How are they doing it? And you'll find that very interesting. You're going to learn a lot, and it makes a lot of the basic sciences feel better as you're doing them. Anyway, we're going to stop there. That's it for enzymes. We're going to hit some bioenergetics next. So we'll pick up with the bioenergetics in the next video.